Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics Podcast. Hello, Steve. Thanks so much for joining us in the podcast. Such an honor to have you.
Thank you, Marwa. It's great to be here.
Thank you. So I'd like to ask you first, how you'd like to define yourself for the audience who may be first time listening to you? How would you like to define yourself?
Sure. Well, I'm a professor of mechanical engineering here at Stanford. And I think of myself as a scientist and an engineer. So I really want to learn how people work, how we can best assist them with wearable robots, and develop technologies that actually go out in the world and improve people's quality of life.
Mm-hmm. So I'm curious about your childhood. We ask each guest about their childhood. How was your childhood was? Because you were very passionate about what you're doing. So I'm curious how was your childhood was.
Yeah, that's true. I love design and engineering and biomechanics. And I guess a lot of this was evident as a young kid. Of course, like many engineers, I loved building things and using all the typical kinds of building toys and so on. But also, I like to get out into nature a lot. And I spend a lot of time in little miniature civil engineering projects like building dams or new rivers and tributaries to Lake Michigan, fishing and hiking and things like that. And I think that's really fed into my interest in how people work, the biology of what we do. But also a deep interest in art, painting and drawing and sculpture that has really, I think, been helpful in our design work as an engineer. And just I of course loved experiments, science stuff, growing crystals and um, baking soda and vinegar and that sort of thing, the kinds of things that my kids now really love doing. So I was really lucky. My parents are not scientists or engineers or anything like that, but they were really welcoming of those experiences into our lives, and I was, like so many people in this profession, I benefited greatly from great teachers and supportive adults. My grandfather was a carpenter. I loved working in the shop. Great teachers in high school, and robotics and automation type courses. So
Wonderful. You're so passionate. But I'm curious, since you have all this kind of, you're so passionate and have all this inspiration from different perspective. And especially when it comes to design or robotics, maybe the question I'm curious, what could be the question when you try to see whether you have already inspiration as you go for niche and whatever? What kind of question comes to your mind before going to building your first robot or what you're already famous for as first step, passive dynamics? But what kind of question for designing? What kind of thing you have to take in consideration or significant element do you think you have to consider while you think about design?
yeah, it's an interesting question. Honestly, when I first started designing robots, and you mentioned this passive dynamic walking robots, that was probably my first real robot as an undergraduate student working with Andorina at Cornell. Honestly, I just saw a video of the thing moving and thought it was really interesting and cool, and I knew I wanted to work with this kind of system, and just interest in the dynamics of the system drew me in. And then that first summer, I was engaged in intuitive, unprincipled hacking. Um, we had a robot that had worked once, but it was really unstable in heading. And Andy welcomed me to the lab and then left for Finland for he spent his summers in Finland. His spouse Saskia studies tiny wasps that live in these little islands in Finland. Anyways, so I was there with the graduate students and a robot that didn't work, and had to try to figure out something to get it to function well. And I drew an inspiration from biology, looking at how humans use their arms, and intuition about the dynamics of the system to try adding arms to the robot, and that resulted in it reduced the fluctuations in angular momentum about a vertical axis and allowed the thing to walk straight, and that was the key trick. But really, it was just sort of swimming in these ideas and trying things till we found something that worked. Nowadays, I take a little different approach to the design of our robots, of course. Most of my research now is in exoskeletons and prosthetic limbs, and really different from these standalone mobile robots. And in robotic systems, very complicated, challenging problems getting legged robots to work, but we have pretty good models of most of the system. And yes, contact is very complicated, friction is complicated, but we have reasonable models. When you start connecting a robot to a person, the human part of the system is the main challenge. We don't really understand how people work very well. And so most of our design process in my laboratory for the last decade has been focused on trying to understand what it is that the person needs from the robot and really answer that question well before we go on to making some product-like device that embeds that functionality to help people, if that makes sense.
Yeah, that's a great point. But I'm just as curious than that. First thing that so you mentioned we don't have deep understanding. What's something for you for the experiences maybe it's still hard to understand, or you can't find a model or how this actually work. Maybe in human, and you're trying to apply to what you're trying to do. What's something is still hard for you to understand? Yeah.
Sure. I mean, honestly, the way that animals work, including humans, it's beyond my comprehension. We're just fantastically complicated, especially in our nervous systems. And we made a lot of progress in some of the problems of wearable robotics. And we can talk a little bit more about some of the design tools we developed for emulators and human loop optimization. But especially when you're dealing with people with a disability, we really don't understand how to help people with most disabilities, physical disabilities, to walk better yet. And this is something that I spend a lot of time thinking about and grappling with. And I hope that we make progress in the next 5 or 10 years. But in a few areas, I'm a little bit stumped, I have to admit.
What could be trade-off when it comes to designing? What you try to do in designing exoskeleton, for example, the design procedure. What is the trade-off that you can't really avoid when it comes to design?
Sure. Well, I think the way that I like to think about this is you can break down the benefits of an exoskeleton, the net benefit, into two pieces. One is what good happens when the device does its thing, when it assists you. That's the positive part. And what's the downside of putting it on before it starts helping you? So these things are heavy and bulky. We try to minimize that, but they have some weight and take up some space. And that interferes with your normal movements. So that's a cost. That's a downside of using a exoskeleton. And then when you turn on the motors, hopefully, if the controller is working well, it maybe makes it easier to walk, helps you walk faster, improves your balance, things like that. And that's the positive. And the net effect, what you care about, is the balance between those two things. So, and in general, the more the device benefits you when you turn on, well, the heavier it's going to be and more bulky, and the higher the cost to put it on in the first place. So we're still trying to identify the best trade-offs between those two factors. And the way we've tried to tackle this problem in our lab is first really try to maximize the benefits. So instead of spending a lot of time working on specialized device design, I know that you've spoken with a lot of amazing engineers and scientists who developed high power density robotic devices and things like that, we have first said, all right, people are pretty good at this, and it's a fun problem, and it's what got me excited about engineering and science in the first place. But the real big challenge that we need to solve first is to figure out what the device should do to help the person. And so instead of making those cool product-like things, we first spent several years developing these versatile laboratory-based emulator systems. So these are tethered to, you wear this little bit of device on your body, but they're tethered to the powerful off-board motors and computers. So you can never take it out of the lab. It's not a thing you can wear around, but you can try out your new idea for what a device should do really quickly. It's a matter of programming some code. And so realistically, when you're really good at using these things, days or weeks of development time before you have tests on a person. And most of the time when you test something, it's going to fail, right? This is a popular area, and you can look at the literature, thousands of papers published in this area every year. And the vast majority, 99, maybe 0.9%, don't actually deliver a benefit to the user in the end, right? So it's okay. We should expect, we're trying to get this desirable effect in a very complicated system, which is the person. Very hard to predict what's going to happen. Most of what we try is going to fail. That's okay. We just need to fail fast, try lots of things so we can find what works quicker. And so first, we worked on these hardware systems to make that easier, and then worked on software approaches, human in loop optimization, algorithms for improving our guesses, so that it's not just the designer that's making the guesses, but we're using the past information of things that we've already tested to, test the most promising next design, so that we can navigate that space a little bit faster. And so that's really where we focused on trying to answer the question of what does the person need before we got to the question of now how do you put it into a device that doesn't weigh too much or occupy too much space on your leg. But fortunately, we're now getting to that point. In the last few years, we've had really, I'm very happy with the advancements we made. For example, reducing the energy cost of walking by 50% compared to device turned off, or increasing self-selected walking speed by 40% compared to device turned off or normal shoes. And so now we're starting to see these really big benefits of the assistance. We've started to shift our focus to putting that functionality into these efficient, low-mass, untethered devices.
But I'm just asking you again, because I think the point you mentioned about asking the right question, I think that you ask a lot of questions. I think that's something I think in research, how we can make sure what we do is beneficial to the user, and that what you try to do. But how you figure out this right questions? For example, because I think in research we have a lot of pressure sometimes to demonstrate something, and you mentioned it would be not useful. So how does this kind of the approaches to solve something that could be beneficial to the user, and figure out the right question or how?
Yeah, sure. Well, we have the benefit in our area of being able to ask people what they want, and we also have our own experience with mobility and have a sense of what we kind of want. And there's a great deal of literature investigating this, this sort of, economics perspective of gait. What do people actually care about? What do they adapt in order to gain? And people care, if you're in pain, people care a great deal about trying to reduce or eliminate pain. If you're at risk of, say, falling, people care a great deal about trying to reduce that risk. Unfortunately, these are really hard problems to solve, and as a field, we've made little progress, honestly, although these are important areas and things that we're starting to shift our focus to. And then there's things that people evidently care about because of the task. They care about moving quickly if you're trying to get from one point to another, and doing so with as little energy as possible. And people do all kinds of little tricks to avoid consuming unnecessary energy, down to swinging their arms. I mentioned that, that the arms on that robot that got me started in research. Well, if you watch people move their arms as they walk around, it's kind of a strange thing, right? The arms aren't um, explicitly implicated in walking on the ground, but we still swing them instead of, say, putting them in our pockets or whatever. And it turns out that movement also saves us energy, just about 7% energy cost compared to keeping them in your pockets. So anyways, so you can kind of infer some of the things people really care about, and then try to make devices that deliver those benefits. And then, of course, before you get to a product that someone will actually buy and use in their daily life, then there's a whole laundry list of problems, practical problems that have to be solved that we're not really grappling with yet. Like, the device should do something sensible no matter what you do. And if you think about all the things you've done today since you got up, walking around and sitting and, I don't know, driving a car, whatever they are, your device, maybe doesn't help you with everything, but at least needs to not make those things harder. And that's a bit of a trick, and we've really not gotten to the point, I think, of being able to handle that wide set of tasks well yet. And probably that's this very applied research that may even happen a lot in industry, in those kinds of collaborations. Yeah.
But I'm going to ask you again to the limitation where we have to go that you achieve what you want for the designing. Do you think the way the designing that you mentioned sometime by inspiration or biomimicry, do you think we have to go something beyond that when it comes to designing artificial parts, for example, in that case? Do you think that's something that the way of the designing should be beyond what we have? Or do you think we can enhance the capabilities of something? Does it make sense to go beyond what we have already? Yeah.
Sure. Yes. So, I think we should draw on inspiration from biology, of course. We should draw on all sources of inspiration available to us, looking at all kinds of machines and designs that people have invented and things that have evolved in nature. But there's no reason to expect that the best way to assist people will be to imitate what people do when they don't have a robot attached to their body. In fact, there's every reason to expect when you change the body by incorporating robotic elements that necessarily the optimal pattern of behavior will change as well, no matter what your objective is. I guess unless your only objective is to imitate the original pattern of behavior, but people care about more than that. So, no, I don't think that biomimicry is something we should hew close to, but it is something we can draw inspiration from. And in many ways, our robotic systems can do a lot better than biology already. Say in terms of power density or bandwidth, the speed of information transfer within the body, some sensing and computation tasks, robots are already way better than people. And of course, there are some things that our robots are really quite bad at compared to biology. I'm sure that your roboticists can have, everybody has their own list, but things on my list include using energy sources that are lying around on the ground outside, or say growing a stronger actuator when you need it, or healing when you're injured. And these are tricks that, you sometimes see the gimmicky headlines in the splashy papers, but we're really far away from being able to imitate those tricks of nature. And I have no idea how we get there, honestly. But if we combine sort of the best characteristics of the human part of the system with the best characteristics of the robotic elements of the system that we bring to the person, then absolutely we should be able to outperform natural human performance.
Mm-hmm. So maybe because we're still listening to, what could be in that case, if you think about short term, maybe challenge or limitation, do you think currently now if you can pinpoint, where it's just like in the hardware, do you think has to have more, like a room for improvement, or where do you think exactly the point we need more to pressure on?
Well, we could benefit from improvements across the board, of course. Um, I still think there is a great deal of basic scientific research that needs to be done in understanding what people need from their devices, especially as you look at, each uh, different population with different disabilities or engaged in different kinds of tasks needs something different from a robot, and we're just scratching the surface there. It's also true that individuals, everybody's different, and in some cases there are really big individual differences. And how do we handle that? How do we identify what someone really needs? And like I said, for some cases we're really stumped, and I would love to see more people engaging with that part of the problem. As we try to, you know, encode these uh, assistance patterns into devices, then of course, better devices and better hardware to draw from and design them would be really helpful, especially in terms of reducing the energy consumption of our actuators. Um, Certain tasks, motors or electric motors say are really good at, like producing power steadily at their ideal operating point, and you can do so with pretty high efficiency. But if you want to produce torque with very little movement, then most of the energy, the electrical energy, is wasted by the motor, right? And this is involved in lots of human movements, holding a posture or moving very slowly under high torque. And so, some advances in actuation technology would be fantastic. And there are a few really promising things out there. Uh, Electrostatic-based motors or electrowetting motors, things like that. Very cool stuff. Not an area of research in our lab, but there's some manufacturing challenges, and I would love to see graduate students take those problems on and take them into their faculty careers. And we've also been working on some approaches using electroadhesive clutches, so also electrostatic, and the benefit there being that once you charge these elements, you don't have to keep paying with electricity. They can hold a pretty high force with a pretty small amount of electrical energy use. And that results in some interesting control problems and systems design problems that we're working on.
Great. So when it comes also to learning, I'm curious about when you work in control learning, or how do you imagine learning looks like when you have, for scenario that you have their own prosthetic part and you just live with that. So do you think there's limitation in learning here, or how do you see this part?
Learning in the person is a really, really important part of this process. We see this. Just completed a study recently. One of my students, Katie Poggensey, where she had people use exoskeletons for about 10 hours, which is a lot longer than most of our own studies or other studies, and observed how people's expertise with the device changed for that time. And when you first put on the device, if we apply our standard evaluation, you see almost no benefit from the device. And at the end of the process, energy costs, in this case was ankle exoskeletons, energy costs reduced by 40%. So you get this huge benefit when you know how to use the device and when it's optimized to you. But that takes time. It took a couple of hours of exposure for young, healthy participants to learn how to use these devices expertly. And so that's a limiting factor on any of these devices that we field. I mean, you're going to have to use it for hours of walking or running before you start to really get the big benefits. And we have to think carefully about how to help people bridge that excitation energy, right? So that they can actually get into the part where it's useful. As we move into trying to apply these same approaches, people who've had a stroke. There's some reorganization of the nervous system that happens following these neurological injuries that could interact with learning processes. And so if a person can't adapt to use the device effectively, then they can't get a benefit from it, right? All the things that we're trying to accomplish are on the human side of the system. So if the person isn't adapting, they are not benefiting, right? And in those cases where learning might be more challenging, we have to really think about a few different ways to tackle that. One is, what experiences do we need to give the person so that the nervous system can identify, oh, I should learn a new approach. And you can try training people with variation training or biofeedback, things like that. We've seen some cases in more basic scientific research where that can be really effective. And the other thing is just making sure that we are assisting in all the ways that are needed in order for the person to adapt beneficially. It may be that when with a person that has a large capacity for adaptation, then just pinging the system over here is enough, and they change the rest of their movement so that this little ankle thing is helping their knees and their hips and everything else. But it might be, if you have less capacity for adaptation, maybe we need to assist those other joints more directly, things like that.
So I'm curious in the process, this experience that you have been doing. If there's a direction, for example, you're supposed to that should work in a certain way or be in the modeling or simulation, and in reality, when you try to experiment it, it was maybe counterintuitive or surprising result. You didn't expect that. Do you have any moment like that?
Oh, sure. I mean, the path I'm on right now is all really a reaction to a big experience like that as a PhD student. So as an undergraduate student, we did this passive dynamic walking robot stuff, and I was excited about it, but, with no offense to my colleagues, walking robots, in terms of the direct societal benefit, so I wanted to try to apply some of these ideas in a way that could really help people more directly. And so I became a PhD student at the University of Michigan and started trying to apply some of these ideas to prosthetic feet. And we had a great idea that we're going to capture some energy that's normally dissipated in the spring, and then later we're going to return it. And our passive dynamic walking models say this should make walking more efficient and save the user a lot of energy. And we had some promising looking initial results with people who didn't have amputation wearing like a simulator boot. But when we, after years of designing different versions of the device, we got to tests on people with amputation, and what we found is that it actually made walking harder, and they didn't like it. So that was a real shock. I coming into this as a young person, you have to be a little bit overconfident to try some of these crazy things, right? And it didn't work out at all the way I had hoped, and really made me stop and think about the whole approach we were employing and how we could do it differently to try to avoid that kind of thing in the future. And hence, really versatile systems where you can try lots of things because you're going to fail, and that sort of thing. So that I see this in a lot of people around me. You have these apparent failures. You have these cases where things didn't go the way you expected, but you learn something really important from that experience that puts you on a new path and allows you to really advance your field or discover something new and exciting. So, yeah, don't be scared of those failures. Look them right in the eye, and learn from them, I think.
I like that. Yeah. But I guess it's in that case about when you mentioned that example, but do you think the concept of having the resilience already? I'm curious in human when it comes to you try to design that in your lab. Do you think the concept of resilience or redundancy had a room that you think maybe can deploy it or not applicable in a scenario like that? Have redundancy or resilience?
Yeah, it's a really good question. how adaptable are people? What, um, how much of a change can we make and still have people learn to perform well in this new circumstance? And that's something we think a lot about, actually. For example, in one of our recent experiments, we assisted hips, knees, and ankles, both legs, with this, you know, big, powerful exoskeleton, optimized assistance, and trained people so they were really expert. And energy consumption was reduced by 50%. But if we throw that same capability into a musculoskeletal simulation model, the model will suggest you should be able to reduce energy costs closer to 90% or nearly 100%. So what's happening? Why doesn't it happen in the real experiment? Well, probably we're missing some things and there's some important functionality that's not provided by the device, sure. But there also might be some limits to how much of a change in coordination the nervous system is ready for or can handle. And as I mentioned earlier, some of these limits in resilience could be evident in our less exciting results so far when applying really similar techniques in our prosthetic limbs for people with amputation or in our very preliminary work in exoskeletons among people with stroke. Yeah. Does that make sense?
Yeah. Yeah. Thank you for sharing that. Yeah. But I guess, again, to the tools, when you mentioned about simulation or modeling, I would like to be curious about this mechanism, how you design that, how you get, if you can, just what could be significant for you. Would you think we need to have more attention, maybe in modeling and simulation tools? What kind of the missing pieces do you think so far? Yeah.
Yeah, absolutely. So there's a really useful and important interplay between experimental work and simulation work and theoretical work. Absolutely. Um, I'm an experimentalist, deep in my bones. I'm a designer. I wouldn't believe the simulation work until I see the experiment that that verifies it. But we can still learn a lot and get a lot of good inspiration from simulations and mathematical models. And just like observations of biomechanics, these are really important elements in this milieu in order to make progress in the design of these devices. So where could we see some improvements in simulations? Right now, our main what we really want are simulations that predict human response to some new assistive device or some new mechanical environment. And we've got very few examples of actually predicting, so not knowing the answer already before you start the simulation, and doing so with reasonable accuracy. Lots and lots of examples of the simulation predictions not matching what happens with real people. So, broadly, we want better prediction from our simulations. And then how do we get that? There are a few things here. I think that probably the biggest problem is our model of the nervous system. Right? The nervous system is so complicated we basically ignore it, or in many cases, or we model it simply as a set of objectives, and we're not even sure about that. So, if we assume the nervous system is trying to minimize muscle activation squared or something like that, then we have enough of a set of assumptions that we can, make some predictions about how the person will behave. But what if the person doesn't care about activation squared, muscle activation squared? What if the person's nervous system doesn't even know what that is? Same thing with energy consumption or some of these other objectives that we talked about earlier. And then the person might behave really differently than what our simulations expect. So that's one piece, is that our model of the nervous system, and even just the objectives that the nervous system is trying to accomplish. We're also our models of muscle they're all right, but we know that they're lacking. We have lots of experimental data that aren't explained by the most commonly used muscle models. And this would be an exciting area, I think. This is something that I'm probably not going to do in my laboratory, but I would love it if somebody out there took a machine learning approach to understanding how muscles work, and just test every conceivable state, um, and measure force and heat rate, and then feed that all into a black box model. That's fine with me as long as it makes accurate predictions. As a thinking about the utility of that kind of tool. I know there are some people that are working on projects like that right now. So I think that's really exciting, and a potential that could potentially make a big contribution in improving simulation accuracy.
Great. But do you think when it comes to the way, I don't know, the perception, do you think it should be the design less depending on the feedback and more predictive? You mentioned but how do you see realistically when you try to have this kind of feedback? Do you think you have to be should be less relying on the feedback and be more predictive? I don't know how do you see the process about the design itself.
Yeah, that's an interesting set of questions there. So, um, yeah, so the utility of a predictive simulation would be that you don't have to do experiments, right? And that would be really, really helpful in speeding the design process. In terms of using measured performance or user feedback out in the world while people are using devices, I think that some form of that will be really essential to getting the most out of assistive devices going forward. And there are some challenges there. When we do this in the laboratory, we usually have fancy equipment, um, these big, $100,000 pieces of equipment that are measuring your oxygen consumption and things like that. And obviously, that's not going to work for a product. Fortunately, there are some ways that we can get away from this. And I mentioned machine learning earlier. I've been really impressed and surprised by how well some of these algorithms can estimate outcomes like energy economy just based on kinematic data from the exoskeleton. And I think it's really promising for um, predicting these, estimating these outcomes in the wild. And you can imagine similar things with speed and so on. For some of the for some things like a person's satisfaction with the device, it's a little trickier because we really want to ask a person, um, questions and ask them in just the right way. But we also don't want to add to the person's cognitive load. It would be very annoying if your exoskeleton keeps asking you over and over again, how am I doing? How does this feel? So perhaps the similar approaches will work there, or maybe we have to discover some new ways of getting that feedback um, without disrupting the person too much.
Yeah, thank you for sharing that. So maybe you can go for the audience question. We have 3 questions. So the first one from Odette, he asked, what advice you would give to what advice you give young and undergraduate students who want to work in biomechatronics?
First of all, go for it. It's really fun and a rewarding path. And I imagine in the next decade or two, we'll see a lot of expansion in this area. It'll be a great place to be. Um, you know, study your dynamics and biomechanics, and find a way to get your feet in a research lab. For me, getting this NSF REU experience as a college student, it just changed my life. Meeting grad students and seeing the kinds of problems that we're working on, how the professor and team talked about these problems and what they were thinking about, this pursuit of truth and trying to understand the world around them. It was life changing. I knew that these were my people. This is where I needed to be. So if you get any opportunity to get into a research lab, I would jump at it.
Wonderful. So next question from Kamar. He asks, is the biggest problems with active prosthetic and exoskeleton is a lack of high density power sources and actuators, like batteries, motors. How much does this affect the future of biomedical devices? Does your lab research about this issue too?
Oh yeah, absolutely. That is a real problem as we were talking about earlier. And of course, the higher the power and force density, the better the energy storage density, the better, right? Any improvements there will be better for not just exoskeletons and prosthetic limbs, but for all mobile robotic systems. So this is an important area of research. That said, we have pretty good power density, better than muscle, than skeletal muscle. And so I think that probably there's a lot we can do with what we've got already if we apply it well. So so don't be intimidated by that. Um, I think with consumer type motors and batteries, we can probably, with the right control, if they're doing the right things, uh, get products that really help people.
Mm-hmm. And he also has a question. User subjective assistive medical robotics need a lot of tweaks after market feedback. They can predict the success of or failure of the product. How do researchers approach this problem without actually commercializing product like this?
Yeah, we can't, right? I mean, so I think this is as a professor or as a graduate student, when you're trying to scope your research project, you want to find an area where it is you're doing something that wouldn't be practically too risky for a company to handle, but that if you're successful, it has the potential to become a tool that a company uses to make better products. So yeah, and some people do research on here in the design school at Stanford, people do research on consumer response to products and trying to predict uh, positive responses and what features people like, and that's really valuable stuff. In you don't see that as much among people with a robotics focus, and I think that's okay. We need to provide those folks with better tools that they can incorporate into products that people like and use. Um, but yeah, it would be nice if we could also more easily field our devices, but it's so resource intensive. Yeah, to make something that is actually solves all the practical problems that you can go out into the world.
Mhm. Maybe a follow-up question for that, because you mentioned the risk. I think that's something interesting. And when you have risk and ideas and also something beneficial, do you think in academia is easy for you to go for risk ideas?
Absolutely, yeah. Everybody has their own sort of strategy or approach to these things. Um, I find it most rewarding to pick a problem that is that is really hard. That and why really hard? Because otherwise, maybe it could be solved by industry. Um, that the solution to which you think could really help people, and then go for it. And avoid the pitfall of publishing lots of little incremental papers or you know trying to bump your H index and all that stuff. That's it's not rewarding. It doesn't fill your life with purpose. You won't be as excited to work on these things, and it's not good for society in the long run. So, um, so yeah, we try to take on those high risk, high reward problems that fit best in academia, and as a result, sometimes it doesn't. You don't get the reward, right? But that's okay. This is part of the deal of academia. And who was it that said, if we knew what we're doing, it wouldn't be research. Maybe it was at Einstein or something. Yeah.
Right. And I have a question also from Sandra. He asks us, because our exoskeleton are intermediary before fully autonomous robots are used in any say task? Or do you see exoskeleton being deployed in spite of robots working alongside?
That's a great question. So for tasks that are really consistent and repeated, stereotypical, then a standalone robot that just does that thing is going to be better than an exoskeleton, right? Um, and for tasks where there's some high degree of variability and there are perception challenges, and you need actual intelligence, not sort of like everything that falls under AI now, but like what people mean when they say intelligence colloquially. Then combining the human with the robot can win. That can be a successful strategy because you have the person who's problem solving on the fly and coming up with creative solutions to the problem, and you have those benefits of the exoskeleton of say enhanced strength or better sensing, better power. And so I think those are great places where, especially in industry, exoskeletons can be really beneficial.
Mm-hmm. And also a question: how do you think exoskeleton advancement can contribute to reducing muscular or skeletal disorder, like reducing stress and vulnerable bones like the spine, etc.?
Yeah, I think exoskeletons are going to prove in the long run to have great potential to reduce injury risk. So if you do a little bit of back of the envelope analysis on the biomechanics of producing a force with your arm or your leg, what you'll quickly see is that the force in your muscles is really high compared to the force at the at your hand or your foot. Like the weight that you're holding is 10 times less than the force in your bicep when you hold something steadily. And so most of the forces in your joints actually come from your muscles, not from the external world or your body weight. So if we can use exoskeletons to reduce the forces in our muscles, that reduces loading in joints and ligaments, and that can help, say, reduce wear or stress-related injury, say, related in osteoarthritis or lower back injuries, things like that. So I'm really hoping, and obviously, it's a very complicated system, as we talked about earlier. It's really hard to predict exactly what assistance will garner those benefits, but I am very optimistic that in the next few decades we're going to find ways that exoskeletons provide that benefit to people.
Mm. I have a question also from Tommy. He asks, I think that's really the first one, but what advice would you give an undergrad student looking to get into biomechatronics by themselves? So I think, I don't know if that's something already covered at first part, but I think, yeah, I don't know if you have any something to add here.
Sure. Well, I mean, the to get into biomechatronics, a great path is develop strength in robotics and develop strength in biomechanics, and then bring them together. A lot of people get into biomechatronics with a heavy foundation in robotics and very little understanding of the human or animal side of the system. And if you develop that strength in the biology, that will, I think, can set you apart, and really you'll utilize it a lot as you try to understand or predict how your tools will affect the user that whose response really matters the most.
Mm-hmm. So tentacles into a few questions. The first one, what could be your aspiration when it comes to your lab and when you start thinking to reach your goals? What kind of aspiration do you have in your mind, or crazy ideas? I don't know if you have any kind of thoughts you have in mind.
Yeah, well, I guess my current life goal in my research is to be walking down the street and to pass someone using a device that is based on technology developed in my laboratory. And they won't know that I had a hand in that, but just to see the tools we develop out there in the real world helping people. And that will be a milestone that I know that we've actually done that. And so I feel like when we started a lab a decade ago, nobody designed any devices that actually improve performance, locomotor performance for people. And over the last decade, there's been a lot of progress made among young, healthy individuals. And I'm pretty happy with our own contributions there. In the next decade, our focus is really shifting to helping older adults, people who've had a stroke, people with amputation. And I'll be really excited if we can get similar benefits in these populations as we've seen for young, healthy people. So that's a big target. And then, then there's like incremental stuff about actuators and so on that we're excited about, but it isn't that sort of long-term vision. Seeing that device out in the real world, that'll be an amazing moment.
And do you think ego is important for you as a researcher? When you have no idea?
Ego is important for everyone. We all need our ego, our id, our superego. We all need a sense of self and confidence in ourselves to try crazy things. Also you need humility and honesty. Something that that I notice that affects all of academia, but I notice in our field a lot is they're pretty strong pressures. This is not exactly a response to your question, but it's something that I think about a lot, and where there's a lot of importance placed on having the thing that accomplishes the thing, the thing that's the breakthrough, and we're developing hardware, and you want it to have been successful, and as we've talked about, a huge portion of the time, the thing that we developed isn't successful. We're working on really hard problems. So but there's so much pressure to have been successful that we get a little motivated reasoning in there. We have this confirmation bias, and we end up maybe overstating the importance of some of the things that we've developed, and I think it would be so helpful for the field and for society for us to be more ready and willing to look our bad results look at those with clear eyes and okay, this didn't work out, but we learned something from it, and we're going to try something different next time and publish those negative results. It doesn't make you a bad researcher. It doesn't mean your research was a failure. Quite the opposite. It means that we really learned something. We've checked something off on our list of candidate approaches, and everybody can learn from that, and then we will make faster progress as a field. And it's much easier to understand the state of the field if we can be more honest with that, more honest with ourselves and each other, I think.
That's a really important point. I'm curious to ask you in that case, where do you think that's maybe the contributing factors to that? Either it's funding or grants or culture. Where does it come from?
Sure, all of those things, right? We have a system that rewards breakthroughs and productivity as measured by certain counting, right? It's easy to count things like how many papers and how many citations and so on. And it's you can understand how this has evolved over the last several decades, but it does incentivize some strategies that aren't in the best interest of academia as a whole or society as a whole. And you if you get on social media and read what your fellow scientists and postdocs and PhD students are posting, I mean, you've got a lot of high stress, there's a lot of pressure, and a lot of self-promotion. And how do we get away from that? I don't have the magic bullet. I don't know, but I think that some of the things we might consider are changing our publication model. I happen to be an editor for a fancy journal, but I think we place a lot too much weight on publishing in fancy journals, and it's kind of a brittle way of assessing impact, because you've got one or two people looking at a paper and trying to guess whether it's important. And maybe it's the middle of the pandemic and they've been up all night with their kid. Maybe their kids are stuck home from school right there, and they're watching the kids while they try to read your draft. And so it's not very robust against misperceptions of these decision makers. Whereas if you say base impact assessments on a broader set of evaluators, by getting the work out there quickly and then getting feedback from lots of people, I think that could be helpful. There's a publication model that's been making its people whisper about in the background for a few decades now, where we get rid of journals and everybody publishes their work, and then the way that you develop credibility is through public reviews. And I think that kind of approach is worth considering. And you see little moves in that direction from some places. That would also help with some of these issues of the financial structure around publication as well.
Thanks so much for saying that. I think that's very, very important point. Thank you. I'm curious to ask you, because we have few questions, what could be the most important quality? Because you're so passionate about what you're doing, but it could be the most important quality you have to maintain while being in academia. What could be?
Everybody's different, and you could be an incredible researcher by bringing really different qualities to your work and field. So I don't think that there is one necessary feature, but in my own work, some of the things that are helpful are having an obsessive nature, finding a problem, and then really just sticking with it, not letting it go, thinking about it day and night. It helps me to go deep and make progress on things. Resilience, as you mentioned earlier, I think it's really important to be able to take these failures in stride and keep going, because you've picked a goal that is important and it's worth it, even if it's hard to get there. It's worth pursuing. Those are a couple of qualities that I think can be really useful.
Great. So lastly, maybe what is the best advice was given to you, maybe, and was life changing, maybe in life or career, I don't know, the advice was given to you? Yeah.
That's a great question. I've been the beneficiary of excellent advice from so many people through my life. I've been really, really lucky. And most of it, little things that maybe aren't generalizable or whatever. Getting advice is great, though. I'd say that's having mentors that you can be honest with, and that you take seriously enough to really listen to what they have to say. That's really important. The best advice I've had from such a mentor in the last decade as a professor was my undergrad advisor, Andrew Ruina. I was a few years into my faculty position at Carnegie Mellon and starting to feel those tenure pressures, right? And my colleagues were very kind, and it wasn't really from them. It was really from me, feeling like, oh, I need to have all these papers, I need to have all this grant money, and so on. And I probably can't use profanity on your podcast, but my advisor said, forget them. You know what you want to do. You know what good science is. You know what kind of professor you want to be. Do that, and forget tenure. And it's really hard to live that advice, but it's excellent advice, I think. If you're pursuing research path because you think someone else will think it's good, or someone else will, you know, give you a certain number of check marks. That's a path to unhappiness and not making good contributions either. You have to find things you really believe in and pursue them vigorously.
That's really that's really deep and insightful. Yeah, I agree with you 100%. Yeah, I don't know if you have any final words you'd like to say since we're closing to the audience listening to you. I don't know if you have any final words you'd like to say.
No, thank you so much, Marwa. This is great. I really had fun.
Thanks a lot. I deeply appreciate your time. It was really inspiring and enjoyable listening to you. Thank you once again, Steve. Such an honor having you.